Hello friends, welcome to the channel of Digital to Real. Today I am going to solve one question which has been asked in GATE Computer Science 2014. The question is based on IEEE 754 single precision floating point format. Already similar question I have solved in my last video. I will provide a link of that one in the description box. Please have a look at it. Now this question goes like this. The value of a floating type variable is represented using the single precision 32-bit format at the IEEE standard. Okay, so there is a floating type variable and that variable is represented by single precision 32-bit format. The IEEE standard uses 1 bit for the sign, 8 bits for the bias exponent and 23 bits for mantissa. A float type variable x is assigned the decimal value of minus 14.25. The representation of x in hexadecimal notation is, okay, out of the 4 options, option A, C164 followed by 4 zeros, hexadecimal. B, 416C followed by 4 zeros, hexadecimal. C, 4164 followed by 4 zeros, hexadecimal. D, C16C followed by 4 zeros, hexadecimal. Please note the question again. So we have a number x, okay, and the decimal value of the number is minus 14.25. It is a real number. It is a floating point number. Now floating point number is stored in a register in hexadecimal format. So I have to find the hexadecimal equivalent of the number which would be stored in the IEEE single precision 32-bit format in the register. Okay, so hope the question is clear. Now let's move to the solution. So floating point is a representation of real number. Okay, the IEEE single precision floating point format, how the format looks, you see the format is of 32 bits. So it occupies a memory of 32 bits, that is 4 bytes. The mantissa is of 23 bits. Lower 23 bits is occupied by mantissa. Then 8 bits are of biased exponent. We write it as BE. And the most significant bit, that is a 1 bit, is for the sign bit. Okay. So for IEEE single precision format, we have a bias value unique to this particular format, and that is 127. When a number hexadecimal value is stored in the 32-bit format, you see the decimal equivalent, we found it like this. Minus 1 raised to s, s is the sign bit, multiplied by 1.m, m stands for mantissa, multiplied by 2 raised to be, bias exponent minus bias. Okay, mantissa is this 23 bit, okay, bias exponent is this value, sign is this bit, and the bias value is 127 unique to this particular standard. Okay, now in our question, so what is there in our question? X is there. X is assigned the decimal value. So decimal value of x is minus 14.25. Now let's write the binary equivalent of 14.25 minus 14.25. So 14 is base 10. In binary it is 1110 base 2. Okay, now for 2.25, that is the decimal value, I have to find the binary equivalent. How do we do that? Now the decimal value is 0.25. If I multiply it with 2, I will get 0.5, where 0 is the whole number. Okay. Actually, here is a fractional part is there. 0.5. So a minus 1 is the position of the binary number next to the decimal point. So a minus 1 is the position just right to the decimal point. Here there is no There is fractional part only, there is no whole number, so it is 0. Okay, 0.5, so 0.5 I will multiply with 2, fractional part I will multiply with 2, I am getting 1.0. So 1 is the whole number, there is no fractional part. So a minus 2 is the position next to the a minus 1. So it is 1. Okay. So 0.25 base 10, I can write it as 0.01 base 2. So minus 14.25 base 10 can be written as minus 1110.01 base 2. So this is the binary value. Now it is stored in the hexadecimal format in the register, in the IEEE single precision format. Okay, so I have to find the hexadecimal value. Now this I can write it as minus 1.11001 into 2 raised to 3 in the scientific format. How? Decimal point, I moved it 3 position to the left. So 1.11001 into 2 raised to 3. Number of position, I moved the decimal point will come 2 raised to that value. Okay, by moving the decimal point to left from right, leaving only one means only one. Decimal point I moved it here, not here. Means to the left of the decimal point there is another 1. Okay, so it is moved in this particular way and this is the value. Okay, so from minus 1.11001 into 2 raised to 3, what we can understand is that we can write it in the decimal format, how it is stored in the register. Okay, minus 1 raised to sign bit into 1 dot mantissa into 2 raised to biased exponent minus the bias value. Bias value is 127, I know, for IEEE single precision format. So what is BE? BE is 3 position, 3 more than 127, that is 130. Okay, so 3 can be written as 130 minus 127. So sign is 1, mantissa is 11001 and BE is 130. Now mantissa is of 23 bits. So what to do with that? Here the values which I have written is 11001 is a 5 bit. So that would be followed by 18 zeros. Okay, so that would be the mantissa value. Biased exponent is 130. So 130, how I can write it? And it should be noted that biased exponent is of 8 bits. So 128 plus 2, I can write it at 2 raised to 7 plus 2 raised to 1. So for a binary number of 8 bits, 1 is in the position of 1 and in the position of 7. So here, so this is the binary value, base 2 value. And this one is also base 2 value. Now I will put everything in the IEEE single precision format in the register of 32 bit. So you see mantissa in the lower 23 bits. So I am writing is as, this is the full mantissa, 11001 followed by 18 zeros. 8 bits of biased exponent and 1 bit most significant bit of sign. So if I write it in the hexadecimal format, grouping the zeros, grouping the 4s, here 1 4, 2 4, 3 4, this 4, okay, then this 4, this 4, this 4 and this 4. So what it is written as, you see, C1644 followed by 40, 1 2 3 4. So C164 zeros followed by 4 zeros hexadecimal. This is the option A. Okay, so this is the correct answer. If you like the video, share with your friends. Please subscribe the channel and have a very nice day. Bye bye.